Welcome to Remtech 2020, session 5. We're really happy to have you with us. Starting with the session on groundwater remediation, I'm introducing myself. I'm Dietmar Müller-Grabher. I'm working with Environment Agency Austria, but I'm here in my capacity as representing a common forum on contaminated land in Europe. Which in its constituency is a regulators network of not only European Union countries, but all European countries, ministries, representatives, and scientific advisors interested in exchanging practices, their new findings, anything they need in contaminated land management. And talking contaminated land management, of course, land. So we see the soil and groundwater. And groundwater is a vital natural resource to us and a big challenge in a lot of countries. In particular, for example, in my country, as we receive 100% of drinking water from groundwater. So groundwater protection, it's different across Europe, but usually highly valued. If you're interested in Common Forum, there is the web page I would recommend. It's Common Forum, just written together, .eu. So, Nicola, may I ask you to introduce yourself and Claire maybe, and Sophie, whatever.
Yep. I am Nicola Harris. Thank you, Dietmar. I work for an organisation called CLARE that is based in the UK. We're a not-for-profit organisation and we are a knowledge transfer organisation. We publish a lot of bulletins, technical guidance for the land contamination industry and the broader land reuse. You can find out a lot about our organisation, plus all our publications are freely available. You just need to register on our website, which is www.clare.co.uk. We also are the Secretariat for the Sustainable Remediation Forum International and UK. Again, all the information is available on the website and you can access it from there. We publish lots of broad publications.
Nicola, you are muted. Just unmute Nicola, please.
There we are. How much of that did you hear?
Some 30 seconds, so whatever you like.
Okay, so did you hear about all of it, or is it just gone mute?
No, it was just recently. So.
Oh, right. Okay. So just go to our website and you will be able to. The host is muting me. So there we go. Go to our website.
Thanks, Nicola. And then it's to me also then I want to express my gratitude to all our colleagues and friends in Italy and in Ferrara for all the effort bringing us together. So I really appreciate your hard work to make Remtech 2020 happen. It's great to be in touch again with all Europe and all the world by your event you're organizing. So grazie mille, Marco and to all. Just introducing the session, groundwater remediation, that's the title, but probably that's an understatement. Likely the next hour and 1.5 maybe, we are very much with forefront running thinking in technologies and approaches how to come up with new solutions for groundwater remediation. So there is something in the pot for there are a lot of mega trends out there that we will need to cope with also in groundwater remediation. Obviously, climate change is one of the most important, so we need to discuss and learn about. Then it's also for the technologies adapting to all the major trends around the globe. It's developing really not only a simple technology, but technology concepts that integrate really a process thinking for coping with the challenges. And challenges, it's very much, I guess, in future, there will be new challenges in new contaminants we have to deal with. And we are still learning about contaminants we already know, that they might be rather more complex in their properties and their behavior in the environment, so that we need to go on to exchange our knowledge like we will do within the next 1.5 hours. Finally, introducing the rules of our session. It's 5 speakers. It's 15 minutes each. I will come in after 15 minutes to remind you. You will have an allowance for maximum 20 minutes, maybe, wherever you stand. So that's fair enough. That will leave us half an hour for discussion. We don't take questions directly to the talks. So,
and Sri Vasulu. The interest I have in this concept of groundwater remediation and climate change has been something that's been developed really for a last number of years in my practice. I've been working for about 34 years as a professional hydrogeologist, as an environmental consultant. And I was lucky enough back in the early 1990s to be involved with a number of solvent remediation sites that were primed for looking at ways to change what we were doing. You know, we all started with groundwater extraction, pump and treat, that, you know, kind of that aggressive, which was fine for some mass reduction, some hydraulic control, but it really wasn't getting us anywhere in terms of closure. We recognized that there were different ways to do things, and so the whole in situ passive remediation world really developed from that. And I was able to work and was the designer for one of the, probably the first permeable reactive barrier for solvents, working with the University of Waterloo, the clients there, General Electric, and others who are within the Solvent Summit. So back then we started to look at resource conservation from the standpoint of remediation. Today, let's flip forward about 25 years, and we're looking at these issues of climate change and the impacts to hydraulic systems and geochemical systems. And we recognize that the things that we were doing before are I would say vulnerable, perhaps, to these changes in hydraulics and geochemistry from climatic action. So that's kind of that gives you the set of everything that we're going to go through here over the next few moments. Okay. What I'd like to also do is start with an acknowledgement of the caretakers of the land. This is a tradition that we do in Australia and also here starting in the US. So I acknowledge the Awabakal people of the land where the University of Newcastle and Callahan is, and also the Miwok people in Northern California where I reside. So today, over the next 15 minutes, why is this different? That's what we're going to talk about. You know, we talked yesterday in one of the sessions about sustainability. We're going to bring that forward where we also add the ideas of resiliency and durability for our groundwater treatment remedies, because that's where we're kind of headed, right? Our designs primarily to date have looked at historical climate records, maybe current, but moving forward is something different. And we have to look at those changes, talk about the effect of that changing conditions on the remedy, and then we'll close it out. My slide right here has a couple of photographs of how things change. This is right almost in my backyard, kind of down the street from where I live. You see the flooded areas that we had a year ago, and just recently this Martian orange sky from the wildfires in California that we are just now clear of. So we know that conditions can change rapidly. Okay, oops. There we go. There is a lot of information out there that tells us about what the climate conditions are going to be really throughout the world. We have information for Europe, for Australia, for North America, for South America. Obviously, moving forward is still, there's uncertainty, but we see these trends. And so fortunately, we have various research and government agencies that allow us to start capitalizing on the information collected on downscale models. And we start understanding what are these trends that we're going to see. So I've just put on one idea here, some information for east coast of Australia, where Newcastle is, and we know that these trends are going to occur. We're going to see changes in temperature. We're going to see increased intensities of rainfall events. We're also going to see perhaps less overall rain, but more of those intensive extreme rains. We're going to see a lot more natural variability, and we're going to see sea level rise in places. The other aspect about sea level rise that's really important for remediation is what is going to be the coincident groundwater rise that also occurs, and there's more information coming on that too. And then we see the intention from the global and national media. This was a New York Times story from just 2 years ago, more than what they were from the natural condition, right? We've changed our drainages. We've changed our ability to infiltrate, think of urban soils, for example. We've brought in different materials from different places. We've changed the carbon content, the oxygen content, et cetera. So the issues about changing hydraulic head today and into the future, sea level rise, groundwater rise, land use changes, this all comes back into it. So one of the areas right now of doing is looking at this conceptual model, changing that out, bringing in some of these newer considerations. We can look at sea level rise. Here's a great example of something, this map in the upper left-hand corner in this area here is the San Francisco Bay region. By the way, I live right about here where my pointer is. So that's kind of where I am. This area in pink is one of the models for potential sea level inundation. Now, it doesn't mean that the seawater is going to come in that far because of land use and all that, but it also could mean that groundwater comes up under these areas. Within these areas are hundreds, perhaps thousands of contaminated sites. These yellow triangles here are where some of those sites are along the bay. We know sea level is rising in the San Francisco Bay Area. So here's what we have to think about. As sea level goes up, for example, as groundwater goes up, if we have remedies for, say, closed legacy sites, what's going to happen to the residual chemicals that might be there from the standpoint of geochemistry, biology, et cetera? And then I want to just quickly bring in these terms. Yesterday, there was a whole session on sustainability. I'm bringing in also that concept of resiliency. That is the ability to recover from these changes. And then durability, which, believe it or not, the US federal government actually did identify 5 years ago from the standpoint of looking at long-term measurable benefits. And so the designs are looking at that. And I just want to put out there this beautiful view. If you haven't walked across the Sydney Harbor Bridge, please do so. It's a beautiful site. There are environmental sites that ring the entire harbor. And the issue of sea level rise, once again, in this catchment is important. It's not just about being green, right? It's about, can we make these systems last and become durable? This is one of my favorite slides from the standpoint of the range of really good, and I'm looking forward to those, because one of the questions is, if these remedies have to last a long time and we can't, say, remove the chemicals or create our risk management protections in a short time, we may have to deal with some of these changes. So the longer in time we go, and this is kind of my point of this box here, the more the changes that we might expect in hydraulics, dissolved oxygen, microbiology, and water quality, pH, et cetera. So this is kind of the key thing about designing going forward. Quick example, the PRB, I mentioned I worked on this for 25 years. This is not a unfamiliar technology. It's been used in Europe, Australia, the US. The issue is we're trying to create this barrier of some treatment material. Here's actually a picture of the very first one that went in back in 1994, across a contaminant plume, use a material, in this case it's zero valent iron, it could be a bio, it could be a compost, et cetera, and create these treatment areas. If the water level changes and we lose capture, we may lose capture of our treatment, right? So that's one of the questions. How do we deal with being able to anticipate this, and how do we deal with actually designing for it? I'm not going to talk today about how to anticipate it. We'd probably take 5 days talking about models and all that and what we're going to use. But I do want to bring in the aspect of, again, that conceptual model and some things we can think about. This diagram you see in front of you is an actual, the as we're using, say, a bioremediation system. Is there a way to encapsulate or protect, maybe remove oxygen with another amendment? Iron is a good one, so that we prevent the oxygenation or the oxic effects, the aerobic effects to take over if we anticipate that happening, right? So we may have a whole different set of these going forward. So let's wrap up here in what we've talked about. thinking about future changes is part of our job. If we're in a sea level rise area, and we're interested, this came up actually in a course I was teaching a couple of weeks ago, the issue of, well, what kind of phyto vegetation should I use on a coastline? Well, maybe there's a salt tolerant vegetation that works just as well as a non-salt tolerant vegetation, but it can actually accommodate those changes in sea level and groundwater, right? So thinking about that for the hydraulic gradient changes to a PRB as an example, which could also be a bioremediation system, looking at redox zone designs to handle those changes, redundancy in our hydraulic capture buffer zones. I think one of the more important things that we have to do, and I think there may be some talks on this later today or tomorrow, if not, we'll make one, is to look at monitoring innovations. In situ redox monitoring on a regular basis, in situ hydraulic monitoring on a regular basis, because those longer term changes, sometimes subtle, is what we're interested to help us. And then finally, I put a list here of references for everybody, the SURF UK, SURF ANZ, ITRC, a number of documents that are very good, the ISO standard from 2017, et cetera. And there's also a state of Washington in the US that talks about resiliency from the standpoint of groundwater remediation design. So I'll finish up right here. Thank you again to Remtech, to Marco, to everybody here. Thank you to CRC Care, University of Newcastle, to Ramble. And I leave you with one of my favorite photographs. I am a geologist. That's what I am. So whenever I can get out into the mountains, and especially in a beautiful place like the Eastern Sierra, where I get volcanoes and glaciers and landslides and earthquakes all at once, you know, that's where I want to be. All right. Thank you very much. And I look forward to our next presentations.
Thank you very much, Scott. Please don't be shy to ask questions to the audience, to start putting them into the chat function, and we will cover them in the session after all the speakers. Our next speaker is Yuri Stein from Alpha Clean Tech. I believe you're in Switzerland, Yuri, and he's going to talk to us about superoxide radical as a green reagent and an ultimate solution for soil and water contamination. So over to you, Yuri.
Okay, thank you. Indeed. So my name is Yuri, and I'm a Chief of R&D Division in Alpha Cleantech. And our company has developed actually a new type of chemical oxidation processes, which is mainly based on the superoxide radical, not like standard procedures, which is already well known and everybody almost know how to apply it. We propose a new type of oxidation processes purely based on those magic radicals, and we will show several possible applications of this. So shortly about us, we pretty much a young company, startup company, which is supported by Hebrew University of Jerusalem, Israel, and they help us to develop our new technologies. This is our team. So shortly about superoxide radical, because I'm not sure that everybody familiar with the termination. I'm not a geologist, I'm just a chemist, so I'm excited about molecules. And in this case, the superoxide radical is one of the strongest radicals existing in our body, and you can see it here. This radical is actually designed to destroy molecules, to destroy organic materials, to change it. And the trick is how to synthetically generate and stabilize it outside of the body, and to use this radical to decompose toxic, or let's say toxic organic materials, or let's say pollutants. So here you can see several applications of our radical. Here we decompose organic materials, and it's a very green process because we decompose any organic material. And in the end of the process, we have only carbonate salt, water, and oxygen. This is the only end leftovers of our procedures. And we also succeed in the stabilization of the radical. Here you can see the EPR spectrum. And here you can see normally a radical half-lifetime, we're talking about less than seconds. But here, based on our methodology, we can keep the radical alive dozens of minutes. And this allowed to us to use this radical even in very complicated, materials as the groundwater, because radical need to reach the contaminant or soil. In addition to this, we developed also in our company a new advanced Fenton process. It's pretty much a standard Fenton procedure with a little bit changes which make it a little bit more efficient. So we propose three types of technologies, three types of solutions, and three types of application: soil treatment, wastewater treatment, or groundwater treatment, and the cleaning of railway ballast. All the processes are in situ or on site, depends how you consider it. So our superoxide radical allowed to us to decontaminate a wide range, efficiently decontaminate a wide range of different organic materials. We're talking about a Betex group, petroleum group, aromatics, polyaromatics, chlorinated solvents, PCBs, dioxins, pesticides, herbicides. All of them can be efficiently decomposed by our methodologies. And the biggest advantage of this is that it's happened very fast. Our methodology is extremely fast. We may be one of the fastest solution on the market because the radical attack is extremely fast. So that's what allowed us to decompose a highly concentrated, let's say highly concentrated contaminated soil or water by, let's say, we're talking about a time of minutes to hours. Here you can see some examples of materials that we treated. For example, PCB decontamination. We can reach more than 90% of conversion in the one single treatment. And also we're talking about diesel leftovers or crude oil. In all the cases, we can reach a very high conversion levels under simple single treatment. And our process is efficient for contaminants from concentration of 0.1 ppm till 100,000 ppm. It's really crude oil spill, okay? Recently, our technology was also been chosen by Solar Impulse label. So they decided that our solution is efficient and our solution is green. We're one of the 1,000 technologies where they choose to promote. And here we can see some examples of decontamination of chlorinated materials. Also here you can see that we can decompose a wide range of different types of chlorinated materials, and the only end products in this case will be carbonate salt, a little bit salt, and oxygen. And also here we can do it for a very high and very low concentration of chlorinated materials. And a little bit about CO2 footprint. Our technology, as I told before, unique in the way that we have a very low CO2 footprint. We are not generating carbon dioxide at all, almost at all, and not like any standard incineration process or oxidation process where you take in organic material, you add oxygen, and then you have carbon dioxide. In our process, as you can see, the only end product of the procedure is carbonate salt. We mineralize also the carbon dioxide. So actually, our CO2 footprint is extremely low, and this was proved by TÜV Germany independent investigation. So this is our technologies against existing technologies in the market. I will not talk a lot about it. I just want to say that our technology is extremely efficient with high conversions, and there is and we can treat all different kinds of organic contaminants. Actually, so far, we didn't detect even not one material that cannot be treated by our procedures. As I told you before, we were certified by TÜV Germany. It's an environmental and efficiency standard. We were supported by Horizon, and that's where we are. We starting first pilots with two Swiss companies, Eberhard and Castle, and one Italian company, Alberti. So hopefully in the end of the COVID crisis, we can start first executions. And this is the picture from the pilots with the results. As you can see here, we started with contamination level of 1000 ppm. And in the end of the process, the soil reached the level of approximately 500 ppm. And for the polyaromatics, we started from approximately 800 and we finished with 25. And also here we can see the same. We started from 1,500 ppms and we finished with 65 to 400, depends on the procedure. And here for the polyaromatics, we finished with 10 to 35. So the technology is really efficient. The technology can decompose also in the real case scenario, in the real soil with all the garbage that you all know you can find in the soil, and it's still working. And now a little bit about the wastewater. We can also decompose and treat organic contaminants in wastewater. If it's a LNAPL or DNAPL, if it's chlorinated materials, we have a running pilot in a wastewater facility, which is running in a capacity of 2.5 cubic meter per hour with extremely high conversions where we can decompose almost all the organic material from the soil. And as you can see in this table, we can decompose chlorinated materials, aromatic materials, and so on, drug leftovers, and so on, with a very, very high conversion rate. And as I told you before, very rapidly, talking about extremely fast procedures. Here you can see a little bit about the kinetics of our processes, decomposition, for example, of T-chloroethylene in the wastewater. You can see that already after half hour, even before, we reach extremely high conversion and we almost done. So some results from the wastewater decontamination. So we worked on one side, actually it was in Italy, with a contamination level of 7,000 ppm, and with our reaction we reached 52 ppm at the end of the process with an extremely high conversion of 99%. It was a 40 minutes reaction only. And thank you very much.
Thank you very much, Yuri. Everyone's being very good on their time, so that's excellent. Moving on to our third speaker, which is Troy Liza from Provectus. And Troy is the Technical Sales Director based in North America and recently joined Provectus. So over to Troy.
Nicola, thank you very much. Appreciate everyone joining us today and the opportunity from Remtech to present. I am Troy Liza. I'm the Technical Sales Director, North America, and also working in Europe as well with Provectus Environmental Products. We are a technology provider based in the United States, but we do have partnerships throughout Europe, Southeast Asia, Latin America as well. My presentation today, new and integrated biochemical electrochemical method for remediation of contaminated groundwater. So as we bring new technologies to market, there has to be a need for it. Otherwise, it's just a novel, hey, we've got a new technology. But if there's not a need or an application, it really serves no purpose to us nor the market. So why is it there's a need for this new technology? If you look at traditional ISCO approaches with chemical oxidation, there's an issue with longevity, how long the amendments are active in the subsurface and treating the contaminants we're looking at. Some of the most effective chemicals that we can put generate the radical chemistry, which Yuri just spoke on previously. The problem with these radical species is very, very short lifetimes in the subsurface, seconds to microseconds a lot of times for some of these technologies. We had heard you earlier talk about doing potential PRBs. That's an issue. Very rarely do you have opportunity or applications of ISCO materials in PRBs. Some of the cylinders or candles that some of the technology providers have brought to market have limited applications, and now you're seeing some potassium persulfate due to solubility that's being implemented. But what we're looking for is a sustainable long-lasting in situ production of these reactive oxidant species that can be effective as a PRB to go after those contaminants. They're not treated by traditional methods, the 1,4-dioxanes, MTBEs, some of the perchlorates. We can also go after and treat deep aquifers. That would be one of the goals we're looking to, as well as those challenging lithologies, those tight soils, fractured rock, karst, those type of materials. So what we've been able to, in a partnership with the El Gressi group out of Israel, Provectus has our Provect EBR ISCO, which can be utilized as a PBR. This is a system that continuously generates Fenton-type reactive oxidant species. Now, being able to do this, we can go after those challenging lithologies. There are certain situations where currently you see sorption or sequestering or use of carbon. That may not be an effective approach, and we want to actually implement an oxidative approach. This would be an alternative to the pump and treat or hydraulic containment operations that are typically long-term with high O&M requirements for the clients and the engineering groups that are implementing them. With the EBR, this is effective over an extremely wide range of contaminant concentration, so it overlaps where other traditional remediation approaches have been applied. So what exactly is this? The EBR system, it contains 3 electrodes, one for production of hydrogen peroxide, one produces elemental oxygen, and the other one generates an iron release. This is borrowed from fuel cell technology, and it mirrors the Fenton's chemistry in the oxidant species that it produces. This is a computer control. You can see on the left-hand side the control panel that controls the system. It is remotely viewable. The photo on the upper right-hand side shows the control panel, or I'm sorry, the continuous monitoring system that we can set up that can be viewed. The photo on the bottom right is actually one of the electrodes plus the EBR reactor that has been pulled from a well for observation and for cleaning. So this technology is patented both in the US and in Europe through the El Gressi group. Provectus has an agreement with El Gressi's group to provide this technology both in North America and as well as in Europe and in certain portions of Southeast Asia. So again, this is similar to electrofentons in the species that it generates. We have a single electron reduction on the catalytic electrode, which generates elemental oxygen. Then on the cathode surface, there's actually 2 electron reduction from the elemental oxygen to hydrogen peroxide. You saw in the previous picture, or in the previous slide, there's a third cell, which is a sacrificial iron electrode, which once it's in groundwater, begins to oxidize, and it's releasing ferrous iron that then can interact with the hydrogen peroxide that's generated to generate the superoxide radicals, the hydroxyl radicals, as well as the hydroperoxyl radicals. And potentially, based on soil types, also be able to generate ferrates, which are also very reactive and able to destroy several types of contaminants. So the way that this technology differs from traditional electrofentons is we're able to generate low-level Fermi wavefronts and be able to generate a lot larger ROI from the reactor emplacement. Your traditional electrofentons is able to generate these species, but only right on the surface of the reactors that are in place. With the EBR, the system generates very, very high ORPs in excess of plus 600, which allows to set up these low-level Fermi fronts, and you get kind of like a Haber-Weiss reaction of a stabilization between the iron 2 and iron 3. It allows it to shuttle electron back and forth from iron 2 to iron 3, which then allows it to continuously react with the hydrogen peroxide that's generated and create these radical oxidative species. So, again, here's, and what we're looking at are, these iron +2 and +3 nanoclusters. This is the unique feature of the EBR and how it differentiates itself from just traditional electrophoretins, and how we're able to generate typically 4 to 5 meter ROI and the potential to have interconnectivity from various reactors to form that potential PRB. And again, we're at those higher ORP levels, we're showing here at plus 850 millivolts. We get that electrochemical potential to allow that single electron shift from the +2 to +3 for iron to act as our activation species. So where this technology has traditionally been used at this point in time, again, this was developed by the Ogresi group out of Israel. In 2019, there were 35 active gas station remediation sites in Israel, and 14 of those 35 were using the EBR technology. As well as we have 2 chlorinated sites in Israel, as well as 1 pilot site at another location in Europe. Of those sites that have been treated, 7 of them have been awarded what they consider clean closure. So they've reached the targeted levels after 1 year of monitoring and operation. Again, this is an ISO certified technology and their manufacture of it, and it is approved by, and actually is the go-to technology by Israeli Water Authority for these active sites. Currently, we don't have a PRB application or applications here in the States. We're evaluating, actually, we've got about a half a dozen sites here in the States that we're evaluating, and we should have one in operation by the end of this year or early into 2021. One quick case study I'd like to go over on the technology. This is the Niev Zednik site in Israel. This is a fully functioning operating gasoline station, groundwater at about 7 to 8 meters below ground surface. It is a sandy aquifer, some silicon clay lenses, and our typical contaminations for active groundwater sites, we're looking at MTBE at greater than 50 milligram per liter, which is pretty high contamination for MTBE, and TPHs of over 100 milligram per liter. Total size of the area, it's about 242 square meter total area. This has both the 3 EBR wells as well as an SVE portion to pull vapor up out of the Vado zone. The one thing, this graph I wanted to show, you can see in March of 17 where the EBR was implemented, you see this very, very rapid rise in ORP from, somewhat slightly reducing conditions to up, between 600 and 800 millivolts. So we get to extremely oxidative conditions in a very, very short period of time. Some of the data from the site, this is samples taken 18 months after our implementation. You can see there were 3 target areas, areas A, B, and C, where the EBR well networks were deployed. You can see on the right-hand side the 3 areas, area A, B, and C, with the TPH levels. The lighter blue is pre-treatment, and you can see the dark blue areas at various depths post-treatment, where we've been able to nearly completely eliminate all contaminations at all depths, both in the Vados as well as in the saturated zone. You see similar results with the MTBE contamination, pre-treatment and post-treatment, again at various depths from 6 meters BGS up to just a meter below surface, which, you know, in our beta zone area. So this particular site, you know, it deployed 5 of the EBR wells around this site. And we ran for, system was operating for about a year and a half. And again, you can see our contaminations, you know, from, you know, over 50 parts to less than 50 part per billion. So we have, you know, several orders of magnitude reduction in our contamination. So again, just quickly, Provectus is a company where we are based here in the States, but we do have partnerships with companies throughout Europe, Southeast Asia, specifically with Claudio and his group, BAW Environmental Engineering in Italy. We're certainly, you know, ourselves and our partner groups welcome to take a look at different sites and review what the needs and wants are for the sites and determine which technologies are warranted. Certainly happy to take questions at the end after all the performances, or I'm sorry, all the presentations. I thank everybody for listening and appreciate the opportunity to share with you today.
Thank you very much, Troy. Right, we have right, we have Hans.
Yes, hello.
Yes,
Yeah,
sorry.
finally.
I thought it was Alberto going to be there, but I think it's going to be Hans. So you work for Geochem Technology, and you are going to talk to us about going with the geochemical cycle.
Yeah, that's right.
So I'd like to hand over to you, Hans.
Thank you very much. Can you hear me well?
We can. We can't see your presentation yet.
Okay, I'm going to start the PowerPoint presentation.
Yes, please. Thank you.
There it is. Oh, and then I have to share the screen.
Yeah.
And let's see, where is my PowerPoint presentation? Can I not see it? Oh my God. Wait a second.
Can you?
Yeah, try to find my PowerPoint presentation. I cannot see it anymore. This is a very bad start of the lecture. Let's see, why is that?
Would you like me to go on to the other presenter?
Oh, there is it.
Oh, you found it. Okay.
Yes. Okay. Now the title of my lecture is, as I said,
we can't see it at the moment.
You cannot see it at the moment.
No.
So then I have to share the screen. Oh. Wait a moment. Escape. Escape. I'm messing it up. And show. Zoom. Where am I? Here. Share the screen.
Would you like me to go to the other one?
Yeah, go to the other one, and
okay.
Then maybe you help me with later with the PowerPoint. I don't know what is happening.
Okay. Kent, would you mind stepping in to give your presentation?
Let's see if, yeah, I'm glad it's not me. Let's see what happens.
Okay, so let me introduce, this is Kent Armstrong. He's going to be speaking about the cost-effective destruction of petroleum hydrocarbon contaminants with expedited residual mass solubilization under anaerobic conditions via biostimulation. And Kent works for TerraStrike Products in North America. Might want to just take your screen off, Hans, if you can not share your, that's it. Over to you, Kent. If you just make your screen full size, that's it.
We got it?
Excellent.
Well, hello, everybody. Thank you very much. I'm going to speak about a petroleum site. And what we try to know, what we do is our whole process is to enhance indigenous bacteria and indigenous microbial populations to do what Mother Nature intended. And in the process, get your rebound out up front, help solubilize the residual mass in low perm zones, get it out up front, get the dissolve phase so the microbes can attack it. So what is biostimulation? It's not augmentation. We are not introducing microbes to the environment. Mother Nature's done that for us. All we're doing is introducing various aspects, various nutrient formulations, other aspects, inorganic and organic materials to eliminate limiting factors to microbial growth. And what we ask in our strategy is we don't necessarily look at what an individual microbe can do. Rather, what we look at is what is needed with respect to the ecosystem to make the microbes produce and operate under their most optimal conditions. In doing so, they will adapt to the existing conditions and utilize the energy available to them, that which we call contaminants, but they'll then utilize that energy available to them as an electron donor, as an electron acceptor, and we achieve very, very low cost, low impact remediation. This is not biostimulation, but I will not ever argue against source zone removal. Biostimulation is a front end strategy as well as a back end polishing strategy. We can enhance basically any current remediation process, augmenting it with biostimulation. TPH Enhance is the product I'm going to talk about today. It's our patent pending product, which contains nitrates. Nitrates provide a respiratory source for heterotrophic bacteria under anaerobic conditions. It's combined with our proprietary macro, micro, inorganic nutrient formulation, which is specifically designed to eliminate those environmental stresses that limit microbial development. We serve as an alternative respiratory source, as I stated, and it promotes anaerobic degradation of various organic carbon compounds, PAHs, petroleum hydrocarbons, chlorinated, non-chlorinated hydrocarbons, and we are currently in research with Battelle for PAHs, creosotes, dioxins, and et cetera. The site we're out in Colorado. It's an upstream abandoned oil production facility. Very out of the, no energy, very hard to get utilities out to that area. They found the release from the tank battery was documented in 2013. Soil and groundwater contamination was documented to exceed Colorado standards. Principal contaminants of concern in the remedial driver, petroleum hydrocarbons, and benzene was the most distinct driver. Purpose was to evaluate biostimulation as a strategy to destroy source zone residual mass. We're going to remove the sorbed contaminants, make them dissolve phase so they're bioavailable, and resolve the continued source of groundwater issues. We're going to do this with a low-cost strategy at a remote site and promote sustainability. We're going to enhance respiration of the indigenous microbial populations, expediting mass reduction, mass solubilization or flux, and in doing so, expedite source zone depletion organically using the microbes that are there. In 2014, there was a lot of efforts out at this site. In 2014, they excavated several hundred cubic yards of material and then augmented it with a carbon additive on the floor of that excavation. In 2014, they developed a barrier, put it backfilled in with, again, a carbon-based additive, about 5,200 pounds. And then in 2014, they performed an ISCO program, which included the installation of 26 injection nodes with a vertical impact layer between 6 and 10 feet. And they injected persulfate in a silica solution about 14,000 pounds. So over 2 years, they put about 20,000 pounds of additive into the ground. But they still had continued residual source mass contaminant concerns. So we came in and we designed a utilization program to use those 26 deployment nodes and deploy additive filled containing TPH enhance. Each sock has about 2 pounds of additive in. So there was 2 events of deployment. So a total of 50 pounds, 55 pounds of additive was deployed over a 20-month program. During that process, that we had 2 monitoring wells. They had 2 monitoring locations, MW07, which is inside the tank battery, and MW04, which is outside the amending zone. Started this in 2017. Initially, with the first unit, with the first deployments, as we're increasing the additive availability, the dark blue line, we see an immediate decrease of the bioavailable dissolved phase contaminant, the light blue line. In fact, BTEX decreased 84%, benzene 91%, xylenes 99.9%. This is because we produced an additive, we introduced it and looked at the treatment zone as an ecosystem. We're looking at this holistically. We were able to get this system going, and the microbial densities grew. As the densities increase, they're actually able to increase their ability to communicate. As the densities increase their communication, they actually start building protective structures if you can maintain anaerobic conditions and provide the proper nutrients and components necessary for this activity to occur. It's the creation of a biofilm. Immediately then after that, as we reach peak, we see peak bioavailability of the additive, the dark blue line, and we see the lowest level of the BTEX in mid-June. All of a sudden, with the increased biological activity, we see solubilization of the contaminant coming out of the soil mass. This expedited solubilization is getting your rebound out up front. And in fact, we had some tremendous increases in the dissolved phase concentrations. And this is where I go, come on, microbes, let's get going. Soon after that, we see, I thought there was another picture up there, but soon after that, as the contaminant itself has been extracted out of the soils and becomes available, the microbial densities are such that they just start, and the dissolved phase contaminants are available, and we realize 99, 97, 98% destruction of the BTEX components and at an end of a 2-year period. The interesting thing is during this process, the microbial populations go away. As we see an initial increase in the microbial populations, but then as we start reaching peak performance, the microbial populations decrease. Whoops, I think this is now we're at MW7. We're at the down gradient zone. And again, we see immediate decreases in BTEX with an increasing availability of the additive. Subsequently, as the additive appears to be exhausted, we see solubilization of that residual mass, very high levels, 500% increase in overall BTEX contaminants. Then in December of 17, there was a 6-month delay between deployments. But in December of 17, we then see, as soon as, again, that solubilization is completed, we see a destruction of the BTEX compounds. We still have some benzene that needs to be addressed. But after a 2,000% increase in BTEX, we saw a 94.5% decrease. So we're getting it out of the soils. We're eliminating a rebound. This is all done organically by the microbes themselves. We're not introducing surfactants. They produce them themselves. If we can reach density levels sufficient for them to communicate, as I said before. So in the performance summary, we saw that the L-NAPL was removed via natural biosurfactant production and by the enhanced microbial populations. We got the rebound out up front. We then saw dissolved phase reductions due to the enhanced microbes using the carbon as an electron donor, realized expedited petroleum destruction. The removal of the residual mass from the low perm zones is organic and sustainable. We minimize remediation costs. Remember, we used about 50 pounds of additive over a 10-month period and had evaluations that went on for 2 years. We maximize long-term compliance objectives by getting the rebound out up front. Contaminant destruction was implemented while maintaining anaerobic conditions due to the biofilm. We were able to remediate and revitalize commercial and residential properties without any above-ground support equipment. No energy costs, no emissions, etc. Very, very passive. One of our hypotheses are, and the reason that we see our sustainability of 6 to 12 months after a single deployment at a petroleum site, I'll talk later about chlorinated sites where we're getting decades of sustainability after a single deployment. The additive enhances the microbial populations, and in doing so, microbes actually change their phenotypic characteristics and stop swimming. They become sessile. They attach to the matrix, become sessile, and start building protective structures within this biofilm. This allows increased communication within this biofilm. And in this process, they then start through horizontal gene transfer, sharing and adapting and evolving over days to the conditions that they're being exposed to at that present moment. We call them contaminants. They look at it as an energy resource. They begin to work collectively, not as individuals, but as a consortium of populations, and actually behave and perform as if it was a multicellular organism. This is a artistic rendition of a biofilm. The biofilms actually grow, mature, and slough off and migrate down gradient. As a biofilm migrates down gradient, it contains this microbial population that is adapted, and if it finds similar resources and similar conditions, will begin the entire process down gradient again without another ejection. They also, you can see scouts going out. But what's most interesting is inside a biofilm, what did I do? Inside a biofilm, sorry folks. Inside a biofilm, come on. Inside a biofilm, water can move 100 times faster than it can in the bulk water surrounding it. Amoebas cannot attack and destroy and eat the microbes. Horizontal gene transfer occurs 1,000 times faster than it does in bulk water. And here's an example out of Seattle, Washington. And what I want to show here is in these pink bars is the microbial densities during the performance of a TPH enhanced process. You can see as the additive increases, the green line, you see an initial decrease in some of the dissolve phase, but also then, boom, a big solubilization at the contaminant level. With that, at the beginning, the pink bar is small. We were at about 10 to the 1, 10 to the 2 population density of the heterotrophic bacteria. At peak bioavailability of the contaminant and additive, we see that density go to about 10 to the 5. All of a sudden, though, as the additive appears to be exhausted, and later down, 2-3 months down the way, we see the population density of the planktonic bacteria plummet. It looks like they disappeared. But during that 9-month period, we have continued reduction of the petroleum hydrocarbons to attain 98.7 reduction on BTEX. Later in this process, as we see the BTEX and the available energies diminish, they relinquish themselves from the biofilm. They become planktonic again, and that's why you see that pink bar skyrocket. They're now looking for conditions and other situations similar to what they just completed because there's no more available energy there, so they stop creating their biofilm. Prokaryotes are older, more organized and experienced than eukaryotic bacteria. We need to keep treatment zones anaerobic. Prokaryotes are ubiquitous throughout the world. Biofilm is the most predominant form of life on the planet. It's just we in our industry haven't looked at treatment zones as an ecosystem, like a pond, an ocean, a tributary, an estuary. Prokaryotes dominate under anaerobic conditions. They were the first here. They're organized, they're experienced. A biofilm development is necessitated under anaerobic conditions. You have to have anaerobic conditions. And in doing so, You enhance the ecosystem of these bacteria so we can solubilize L-NAPL. We use organic contaminants as electronic donors. TPH maximizes unicellular activity. I'm going to skip this slide real quick because I'm going to leave you with this. Many bacteria can ferment organic compounds. I said the same thing yesterday, but most cannot touch hydrogen. Many archaea, the methanogens, can ferment hydrogen and carbon dioxide, but they can't touch organic compounds. And this is why it stalls oftentimes in petroleum hydrocarbon reduction. But if we can establish a syntrophic relationship between the two, like we do with TPH Enhance, within a biofilm that the microbes themselves establish, Mother Nature's microbes, the indigenous bacteria, we create a consortium of these populations so they can use their waste as an energy source. And they work syntrophically so that they create a consortium of bacteria to do long-term, to do contaminant destruction the way Mother Nature intended. There's a lot of options out there. All I ask is that you give us an opportunity to look at your site and provide you with an option and a potential organic, sustainable way to address your long-term compliance issues. And if I have, do I have 1 minute maybe, or 30 seconds?
Yep.
To some of the things Scott said, and I think it's really, I said earlier, we're a front end as a on its own remediation system, but at the same time, we're a polishing system as well at the back end. After pump and treat systems have reached asymptotic levels, we utilize our additives and established infrastructure to try to go out and polish those residual mass that physical removal won't work. But my point here is, what is the effect of climate change? You know, and it's something we're looking at as well. Some feel prokaryotic bacteria are a single species. It's just one species that just has an incredible ability to adapt in hours. And in doing so, our thought is, if we can create these microbial populations, they're going to migrate with the changing groundwater levels. They're going to go up and down as the groundwater levels go as well. And because they can adapt so quickly, maybe they will be able to adapt to climate change much, much faster than what we see with eukaryotic bacteria and plants in us here on the surface of the planet. So my hope, and then the other thing is, working with other strategies, we could provide low impact strategies that maximize everybody's. Stop pigeonholing. Let's do the treatment trains. Let's look at a strategy that maximizes one technique with the other, so that the two combined are more than the two separate, if that makes any sense, if I said that correctly. So I'll leave you with that, and thank you so much for the opportunity. I, as you know, I love to talk, and I can do it forever. So everybody have a great day, and enjoy the rest of it. I'm on again in about an hour. So thank you again. Have a great day.
Thank you. Thank you very much, Ken. So Hans, have you managed to, you're on mute at the moment?
Mute, so
No,
there I am.
right, you're off mute. Are you able to share your screen?
Well, I'm able to try it.
Okay.
There we go. And now I have to be here. Okay. And then I go from, oh shit. Ah, this is, I have still problems.
You still have problems?
Yeah, but not, let's see. Now my mouse is no longer working. I cannot even see. This is horrible.
So Hans, I can try to share my screen and you follow my presentation.
Would that help, Hans, if Alberto shares his screen?
We can try.
Try that.
Yeah.
I don't know if Hans could hear you.
Yeah, I can
All
hear
right.
you, and I'm going to try to do it again.
Uh,
Can you
Al-
see my this?
Alberto is
Okay,
offering to
here I
share.
am. You see me?
We can see you. Yes, we can't see your screen.
You cannot see my screen.
No, but Alberto could share his screen. There we go.
Okay, then I have to give me a second to get out of my screen again.
Now we see your screen.
Otherwise,
Right, we can see yours. We can see your screen, Hans.
okay, so it's good. Now let's then. Excuse me for all the problems, and let's start
Okay.
again.
So I would like to introduce everyone to Alberto. Sorry, Hans Zylstra from Geochem Tech, and he's going to talk to us about going with the geochemical cycle.
Yes.
So
Okay.
over to you, Hans.
Thank you. Well, you heard also the name of Alberto. Alberto is going to do a project together in Italy, and I will talk about that during the lecture. First, I want to introduce the geochemical cycle. Most of you are acquainted with the geochemical cycle. We have long cycles that take about 1 billion to a million years, where, let's say, for instance, heavy metals are forming ores in the lithosphere, and then they are coming to the surface. They disperse when minerals weather, and then they are buried again to concentrate and complete that cycle. And we have short cycles which occur in the soil, and these take years to centuries. And here we see that microbes and plant roots together, they take metals from minerals, and then these get into the pore water, and they are concentrated again as new minerals, and then the cycle is closed. Geochemical technology it concerns working with minerals to control the, in this case, heavy metals in the soil. Geochemical technology is not new. You can say, for instance, that Hannibal, when he wanted to cross the Alps, used the geochemical technology to make passageways, heating limestones and using vinegar to split the stones and get through on his way to Rome. We use geochemical technology in mining waste management, because the mining waste management that we did is always outside in the open environment and in remote areas, far away from electricity and from let's say skilled workers that can supervise the site. So what we do is we try to use minerals and passive treatment technology, and then blend in the environment. Here you see the bacteriology side about I want to talk later. Okay, now we go to the next one. In Sardinia, we have 70 million cubic meter of acid mining waste, and there is 20 million cubic meters of alkaline red mud from a bauxite refinery. When you combine both, then you can neutralize the acid waste with the heavy metals and immobilize these heavy metals, and then you have something that is not longer dangerous and doesn't contaminate the groundwater. Therefore, we built a small plant at the bauxite refinery residue, where we mixed solar salt plant brines with the very caustic red mud, because you want to have, when you do geochemical technology, mineral reagents that react rather slowly, because if they react very fast, the minerals that is going to precipitate as a consequence of the reactions are very small and abundant, and that's what you don't want. That you want to have a low surface area and contact with your environment if you want to immobilize heavy metals. It's better to have a few big minerals, and that's why we had to decrease the reactivity of the red mud by mixing it with the seawater or the solar salt brines, and in that way you remove the very soluble sodium caustic sodium minerals and replace them by calcium magnesium minerals, which are much more slowly reacting. We also made granules in a little factory out of the slurry of the red mud. To give you an impression of what you can do with that mineral material and the economic viability of it, in Portugal we used the red mud powder and mixed it with water from a tailings dams from a dormant zinc mine, which had extremely high metal concentrations, as you can see, in the order of 14 grams of iron and 10 grams, 2 grams of zinc. And if you treated that with the normal treatment, for instance, with lime, then your whole water was forming a gel. But we were able to pump up that water and then mix it with our transferred red mud and then spray it again over the pond, and then let's say the very dense, very fine-grained particles, they captured the metals in their boundary layer while sinking to the bottom. And so we were left then with a bottom of stable mud with the metals, and you could discharge the water easily. In this project, we were economically viable with a price of $100 per ton of this transformed red mud. We also used pellets of red mud, cemented porous pellets of red mud, and these we used below mining waste. And as the water percolated through the mining waste, normally you get out very high concentrations of metals. For instance, zinc at 700 milligrams per liter in the percolate. But if you put these reactive mineral pellets below that waste, the zinc concentration is almost zero coming out. And in this case, I show here the zinc, but we did the same test with arsenate, and then it appeared that the efficiency of these red mud pellets is about 20% of the efficiency of, let's say, the most efficient commercially available arsenate removal, which is a granulated ferric hydroxide that costs 1,500 euros per ton. So here we showed that with our red mud pellets of 300 euros per ton, we can compete with the industrial material. And we have also the advantage that because our material is very crystalline, it will not recrystallize, and the arsenate will stay on it, and it is, let's say, stable on the long term. This is something I want to show. Is very interesting. You can also use these mineral reagents together with electricity, in this case electrokinesis. What we did is we put the alkaline red mud, transferred red mud, near the acid electrode of an electrokinesis system. And normally the negatively charged complexes, like for instance chromate or arsenate, they moved to the positively charged anode, but then absorb prematurely on the acidified soil. But if we use the let's say alkaline red mud near the acid anode, we see that most of the chromate and arsenate is moving out of the soil into the transferred red mud, where it then permanently binds. And if you calculate the cost savings, then you see that you save with 1 ton of red mud 1,500 euros of electricity costs to have the same result as without the red mud. So now we have already 1,500 per ton for the red mud. Now, the problem was just when we were ready to start the biggest project that we had for a company together with Montana, the remediation, first big remediation of a mining site in Sardinia, the red mud, let's say the bauxite refinery, was put on hold, and we had to close our red mud plant. And in a very short time, we had to develop new materials that had the same qualities as the red mud, but they were made out of industrial minerals. So we bought various industrial minerals on the markets and mixed them in order to get something like the transformed red mud. That means, in this case, this is a lead arsenate mine where we had to raise the pH to precipitate the positively charged heavy metal cations, but at the same time prevent the leaching of the arsenate, which is negatively charged. So we had also to add something to increase the surface area for absorption of arsenate. We had here we constructed let's say a small internal permeable reactive barrier around a slotted pipe that discharged the leachate of this disposal site to the environment, and we mixed all the material with our new mixture, alkaline mixture with high absorption rate for arsenate. The problem was that it was so potent that we could use, we had only to use a few kilos per truckload, so we had continuously to analyze the material that was dug up and calculate exactly how much had to be done, had to be mixed in with the truck and added manually to the truck. Outside of that disposal site, we had to build a permeable reactive barrier, a small permeable reactive barrier, because there was no space. So it had to be small and very efficient. The water coming out of that, let's say, disposal site had extremely high concentrations of zinc in the order of 400 milligrams per liter, and also cadmium was very high. And that was problematic. But we arrived, let's say, we were able to reach the discharge limits, which were only in an order of ppb, and for zinc 100 ppbs, and let's say we could do that because also the let's say the percolation rate of the water was not so high. There were a few cubic meters per day. And let's say after half a year, we switched filter material when it exhausted. We observed that the beginning of the filter started to clog with aluminium gel, and the residence time and reaction time in the filter decreased. And then we switched to the other filter. Water flowed from compartments over and under the septa between them. Now, what is next? Next year we're going to do another treatment of mine gallery water, which we did before, and where we observed that we could also treat this water at much higher velocities than of tens of cubic meters per day, but there were also lower, let's say, heavy metal concentration, only a few tens of milligrams. But we succeeded to treat that also only, let's say, during winter storm, or just after winter storms, we had situations where there was a tenfold increase of the concentrations in the water and also a much higher flow rate, and that was problematic for our filters. They couldn't handle that properly. Later they regenerated with lower flow rates and worked perfectly, but now we have to, let's say, do better and improve this with new materials, and that's what we are going to do. We're going to use improve the filters, make the materials a little bit more reactive. We're also going to use local materials to make our granules, so that we can save the high transport costs. And what we're also going to do is to teach the local operators how to operate our filters. So we must have more readily accessible protocols to operate these filters. That's all what we are going to do next, together with Montana. And another thing we want to do is, I hope we can do, that is use that spent filter material in other treatments, because it is still very, very reactive, not reactive enough to maintain the strict discharge limits in high flowing water, but certainly reactive enough to, let's say, treat the percolate in, let's say, solid mining waste or in soil, which flows at much lower rates. And we did already some tests to prove the concept. Treating waters of this mine by Mount Evacuous flows at 50 liters per second and has 1000 milligrams per liter zinc, and you cannot treat it here because there's no space, but maybe we can let's say filter it with mining waste mixed with our pellets, and we tested that and were successful on very small scale. Now finally, I want to conclude with the picture here of a mine in Turkey, which I made a plan for, where we can see that if in these abandoned mining sites, after tens of years, nature has already done its work, and these what we see here is, let's say, an overfilled tailings dam with very toxic zinc and lead material, which has been strongly eroded and has a dip, which means that it is adapted to the local dynamics of the water flowing. And let's say all the easily removable and erodible and leachable parts are gone, and what is left is something that doesn't leach and erode as easily. So now you should not, I think, start to dig this up and then reactivate it and deposit it somewhere else to make another problem on another site. You must leave it here and then cover it with reactive minerals like I showed you before, and make sure that the water can flow through them, and that we make a soil out of the waste that is in this area, and cover this waste disposal site much more adapted to the dynamics, and then going with the geochemical cycle instead of going against it. And this was what I wanted to say in this lecture, and I thank you very much for your attention, and I hope you go well with your own geochemical cycle. Thank you very much.
Thank you very much, Hans, for your presentation. We got there in the end, which is fantastic.
Yeah,
So no, it's brilliant that we got through. So all our speakers of our session, if you just bear with Dietmar and myself, there are quite a lot of questions that have come through on the chat. Just checking Dietmar's. There we go. Dietmar's there. Do you want to take some from the top, Dietmar, and then we'll go through?
I would like to suggest that we really then go in the order of the presentations again.
Yes, yeah. Absolutely. Yeah.
So, and first and foremost, thanks to all the speakers. So I was not over-promising. It was really, really very interesting. Also the ending in terms of scales coming from the microbes to the big scale problems in mining. Very impressive. Again, for all the participants in the meeting room, you are encouraged to still raise questions. We will deliver them to the speakers. And we right on start with Scott, who was the first. So we move back to West Coast, US. And the very first question coming in probably was from France. So it was, making a guess, Jean-Paul Renaud. Question is, Scott, whether climate change wouldn't even be more relevant to the risk assessment processes, where the conclusion of the need to remediate are made on past and current conditions and extrapolated in the future. So it's in general, do we need to really consider risk assessments of sites we already finished? So
no, thanks Dietmar, and thanks Jean-Paul. It's a very good question, and I think it's very consistent with the idea of looking at the risk model, the conceptual model, in terms of the life cycle analysis, right? It's in that same world, and we might find, in fact, that yes, certain sites today might be protected. They've met their risk management goals. The question is, will they in the future? In the past, we maybe had limited technical ways to look at the future. Today, it becomes a little bit more of an issue with respect to some of the environmental climate changes that we're seeing. So the question, Jean-Paul, is right on from the standpoint, this still everything that we're doing, and by the way, I want to commend all the speakers today. You guys were great. These are really, really good presentations, and all very consistent. They all tied in really well together. It is about looking at that risk management profile. Some sites may not need to be on that aggressive, assessment, but in the future it might. I brought up the issue about rising groundwater under closed sites, for example, and what does that mean? And then I go back to what Hans was saying at the end. Perhaps some of those sites aren't as the chemistry has changed enough so that the mass flux coming off them won't be as great. So maybe we don't go in and try and aggressively deal with them, but we still have to understand that overall geochemical and biological conditions so that we can make those right decisions. But yeah, it's the correct question for sure.
So you agree completely, it seems. That's great. Well, there's another question coming from Fabrizio. Just need to, where is it here on my screen? Sometimes I also get lost, so that's a relief for Hans, probably. Yeah, it's, well, referring to the presentation and, well, about long-term hydraulic transients. He asks simply whether your experience in consultancy, what do you think are the concrete actions to be implemented to have a transient approach rather than a stationary in remediation projects? So what are concrete actions you would suggest?
Yeah, no, another good question about looking at transient analysis. So I was taking down some notes here, and looking at the alternative analysis for a given site and the longer term, I would look at it goes back to that conceptual model again, and the mass flux conditions, both today and moving forward. And so it's mass flux over time, which is going to be key, and that helps you with designing the different scenarios from a transient hydraulic perspective, which I'm comfortable. We've been as an industry developing the various three-dimensional and multi-dimensional models over time, now including recharge issues from groundwater or from rainfall, for example, and that leads into the risk profile, both today and into the future. So it goes back down again to mass flux, and how does that line up to the risk analysis that one needs. A real issue about I also want to tie in these comments that were mentioned by some of our speakers, by Kent, by Troy, by Hans, by Uri, even from the standpoint of it's not just the hydraulics, but it's also the geochemistry, how that changes over time, how the redox will change over time in an area, and then also the biology, as Kent was talking about, because that will adjust. I don't know if you can see it. This is a zeolite, clinoptilolite, that was used for in a PRB. We look at this and how this is going to last over time, and believe it or not, I still have, I don't know why I have this thing, you can't even see it with my green back screen, but this was some of the original iron from one of the first PRBs that was built back 25 years ago and is actually still active today. And the reason that it's still active is because of construction that almost, I would say, this goes into the question, decrease the aging of this material to the elements over time, right? And for the biology, Kent, I think what you were talking about as well is how do you keep that biological community intact as things change? You have ways to do that. I think from the geochemistry, we can do that as well. So I've probably gone beyond his original question, but mass flux, looking at those transient changes, which with our various geochemical and hydrologic models, and then putting that into the different scenarios by which to assess their performance over time.
Okay, many thanks, Scott. So I guess from the audience, that's more or less the questions that have been there. Nicola, do you want to take
Yes, going down to Yuri, I think was our next speaker. So we have a question from Matteo Cassio, asking, would superoxide radical be effective on PFAS And do you have any experiences of treating PFAS?
Okay, so like everything with the PFAS, it's a complicated, it's a complicated answer. Yes, we try to decompose PFAS. Yes, we have some successes, but the biggest problem is that the required limits is in the ppb range, and so far our analytic methodologies is not allowed to us to work in the ppb range. So
Right.
we can do it. So yes, we have some experience. Yes, we have some successes, but unfortunately, it's in the dozens of ppms and not in the ppb level, which is required.
Okay. And one question from me, do you have an issue on the batching up, the scaling up? Because obviously you're new technology and you're working on batch sizing. Are you foreseeing any issues with scaling up for larger projects?
No, we already actually developed our scale-up machine, and we already did several pilots, so we already know how to work with the tons and dozens of tons and cubic meters and so on.
Okay.
To add, Nicola, because there was a second question. We
Can't hear you, Dietmar.
Your microphone's bad.
Yeah, your microphone's bad.
So then try to move on.
It's just your microphone. Okay.
So it's not improving.
Yeah, it's quite faint. Okay.
You are trying to leave.
Oh, there. You are. That worked. Anyway, I'll keep going. So, another question for Yuri and Troy, or Troy. Let's go for both. Do you have any information on the mobility of the radicals in soil or groundwater, and do they need to be in direct contact with the contaminant, or are they able to travel some distance from your injection source? So go to Yuri first and then on to Troy for both your technologies.
In our case, we know that they can move, and they can move pretty much long distances, because in the conditions that we generate those radicals, they can survive dozens of minutes. So they can move, and they can move far away from the injection well. But normally, as far as I know, it's not the normal situation of the radicals.
Okay. And Troy?
Yeah, I would agree with what Yuri said. Typically, what you see with radicals is a very, very, very short-lived, reactive species. We do obviously, to attack the contaminants, we do need to get our radical species in contact with those contaminants, so they do need to travel. Which with our case with the EBR, what separates it from the electrophoretin generators. We're able to, with interconnection from well to well, from our reactor to reactor, we're able to, transmit and continually generate those radical species over extended distances, and create a large, network ROI, so to speak. But they do need to come in contact with the contaminants in order, obviously, to create the destruction we're looking for.
Okay, thank you. Moving on to Kent. The question for Kent is, how is the TPH enhanced delivered to the soil? Is it delivered through the monitoring wells or injected via direct push or other methods? And also, is this a viable approach for a site with very low permeable zones which are holding the contamination, and is it enhanced or more effective in high permeability flow zones? And do these zones need to be targeted specifically?
Well, with regards to flow, yeah, you do. The design is going to take in flow accounts. As just noted, this is a contact sport. And not only do the bugs need to get in contact with the additives, but they also need to get in contact with the contaminant as well. So distribution is the issue with in situ remediation. And that goes back to your CSM. how accurate is your site conceptual model, and that helps anyone who's doing remediation design a process by which it enhances distribution in situ. For TPH Enhance, both of our additives, TPH Enhance and the one I'll talk about later on chlorinateds, are very, very thin. TPH Enhance is so thin a driller's pump won't carry it. So it's amenable to deployment in basically any way you wish. You could, we try to use existing infrastructure as much as possible to save costs. But here in the States, deploying directly into a monitoring well is considered cheating. And so you could do that for a treatability test, but you can't necessarily do that for full scale unless you're willing to take the option of not using that point as a monitoring well moving forward. There's arguments about that. There are some states that I can put 9 injection nodes within 2 foot of a monitoring well, and that's not called cheating. So I'm not sure what the difference is there, but that's a whole nother story. But in terms of delivery of our additives, subsurface galleries, direct application to an open excavation, direct push, any way you want to put it in, it's extremely amenable. And the thinness of our additive, TPH Enhance, facilitates distribution into low perm zones. And actually, the smaller the particle helps propagate some of that further in to the low perm zone so that it can help with the diffusion out of the contaminant through an opening and a biofilm. And we're in the process of doing research right now with Brown University for that exact very thing, trying to demonstrate some of the stuff that was performed out of Colorado State with the low perm zones in the box. I can't remember his name, but in the box. But
Tom Sale.
So yeah, Tom Sales, Dr. Sales, yes, correct. But no, it's incredibly amenable to any application method that you wish. Okay,
thank you very much. There are other questions for Kent, but I think they will have application to other of the speakers. One of the issues often is about biofouling. Is that an issue for any of you, Troy or Yuri or Kent?
Well,
does that?
If I'll just go real quick, there's a very, very big difference between biofilm and biofoul. Biofilm has to be generated under anaerobic conditions, while biofouling occurs under aerobic conditions. The issue with any reducing process in situ is we're creating, especially with my products, I'm creating an extremely nutrient-rich slug of anaerobic area. A pump and treat system, for instance, is very fast-moving, very low nutrients, very highly aerobic. If my nutrient slug comes in contact with that highly aerobic zone, the aerobes are going to go nuts. And that is what produces biofouling to that well. And it behaves incredibly different. It adsorbs things different from what a biofilm does, which is enhances the transmissivity of materials, as well as creating an in situ bioreactor. It creates a nutrient recycling sink.
Okay. Does anybody want to add anything to that at all? One of the questions also is around temperature. Obviously, you're all talking about different situations of applying your materials. Is there an issue with frozen ground, this sort of thing, or what effect does temperature have on the process?
Well, we believe microbes do cycle with the season. They do show seasonality. We've never seen a stall through the winter. We've seen a delay in performance if injected in a winter. Here in New England and upper portions of the United States, in Canada, it gets cold. But we've never seen a stall in the winter. And if you inject spring, summer, fall, it just keeps right on going. They'll just go right through the season. But one of the other things about our additives is when mixing, they do not change viscosity with temperature. So you can be, the viscosity of TPH Enhance at 40 degrees is the same as it is at 82 degrees, which further enhances distribution and injection processes.
Okay. Okay, I'm just trying to flick through. I've lost my buddy. I'm down to one now. Okay, and we've covered about biofouling other than detached. So Robert Wagenveld, what is biofouling other than detached biofilm, which you've mentioned the distinction between the two. Another thing is that adding nitrate doesn't create anaerobic conditions, just anoxic. In which ORPs are you working?
Still anaerobic,
Anybody?
it's not methanogenic. Yeah. And what we're doing is providing a respiratory source so the heterotrophic bacteria can operate under anaerobic conditions. We are definitely raising the ORP, and in the process, we're going to allow those indigenous microbes to utilize any iron, manganese, sulfates that may or may not be present in the system. We don't include those in our additive. But it's just that we don't use oxygen to bring it out of anaerobic conditions. Oxygen is a biocide to biofilm.
Okay. Okay. One thing, sorry, going back up to something for Scott. He mentioned about resilience. There was just to make the audience aware that ITRC have or are in the process of publishing a new guidance document called Sustainable Resilient Remediation. So that's something that people should look out for regarding resilience and taking into consideration cope with climate change and issues with rising sea levels.
Yeah, there are some good documents that have come out, including the SURF UK, for example, looking at the new guidance and the indicator parameters and trying to look at this going forward, which you're right, I think is on the SURF UK website now.
Yeah.
You can go and look.
Yeah.
The state of Washington in the US in 2017 came out with a document about adaptation and resiliency for remediation systems, and provides I would almost say a categorical look at here are the areas to consider as you're developing your alternatives analysis. I believe ITRC is doing something similar. They're moving that ball forward a little bit. The part that's missing, and this is one of my areas of work and interest, looking back at what we've done before and then going forward, then goes into the technology design and the engineering aspects, by which, they're very specific, I guess, design tricks, if you will, from modeling to looking at the geochemical cycle, the biological cycle going forward. What are those specific changes maybe to a matrix for a reactive barrier, or what kind of biological system, as Kent and others have talked about, should we look at going forward? How might the biology change over time, and are there things that we can do today or how to monitor for? And so that's the next step even after these current documents. So it's progressing nicely, right? Question is, will we have time in some cases by which to deal with that? The one thing that we can't do very well and probably need some additional thinking is those exceptional events, right? Those extreme rains and floods and all those things which give the shock to the system. That's almost on a different time scale. It's a shorter time scale that we have to typically deal with. But I anticipate we'll have to, we'll still have to deal with that going forward too.
Yeah. I know in the UK we're doing quite a lot of work on the impact of a lot of landfills around the coastline, and there's some research going on in there as well. So so we've just had another question from Kent to everyone.
Oh no, I'm sorry, I was answering your question. I'm sorry.
Oh right, okay, sorry. I'm just trying. Okay. Do we have a couple more minutes left? If anybody wants to, Dietmar has sent his apologies. He's got technical issues. So if there are any more questions that people would like to ask, or any of the speakers like to talk to other speakers, because you don't often get a chance to ask any of the other speakers questions coming from.
Can I ask a question of
parts of the
Troy?
world. Please do. Yes.
Yeah, Troy. My question: in the units that you've developed, have you tried to monitor the distribution, say, of hydrogen coming off of one of the systems within the and the persistence of it?
Typically, hydrogen is not one of the species that we're monitoring as we go. I'd have to look at the reactions to see what information that would give us. I mean, typically we're looking at ORP, pHs, and conductivities to kind of give us an idea of how we're propagating throughout the subsurface. What's your thought on what hydrogen would provide us?
Well, I'm just trying to understand your system. You're essentially, in some respects, splitting water, I guess you might say, in some respects. You have your oxidative and your reductive system. We know that hydrogen is so valuable for biology and reduction and all that. So, and when I'm looking at the iron system, for example, that corrosion of iron produces a nice hydrogen front, which is helpful. So that's why I was interested, because I think what you're doing is extremely valuable, and maybe one of the tricks, for long-term changes, right? If you can, it's easier to put in a unit or inject a material than build a large wall of something. So
Right.
it allows maybe some of that that flexibility and agility, right, in a given site. So that's why I was interested in some of those other geochemical
Right.
contributions off of the unit.
Right. Yeah, and I'll go back through and look at the sites that are active currently, and talk with our colleagues over at the Al-Gressi group in Israel. I mean, that's the one advantage that we have, and we're creating the most reactive of species without having to inject any chemical whatsoever, and be able to continually propagate those species over and through challenging lithology. So that what else is being generated, hydrogen specifically. I'll talk with our group and see what value we would have there.
Okay. We are coming to the end. Sorry,
I have
Marco.
a quick question for Hans.
No.
Hello, Hans. Finally,
Marco.
you managed the problem of sharing. No,
Yes, thank you.
is about the mining sites you have shown. There is any possibility to that some of those mining waste could be considered as a resource for that there is a debate in the European Union on critical raw materials. Did you investigate this aspect also in your work with Alberto and Montana?
Yes, we did. Let's say we have not really focused on it, but when you are treating your waste and you're mixing it with reagents to immobilize the metals, then automatically you start to think, is this a good idea? Because if you immobilize too strongly, you cannot do a leachate of these wastes anymore to get the metals out. So in the future, I would say we have to look at ways to prevent, let's say, the contamination of the environment while not immobilizing the metals completely in the waste. So that's a very interesting topic to do. The same with the red mud is also a source for, let's say, rare earth elements. And also that is something, let's say, you have to consider. You can use all your red mud to treat the mining waste, but maybe a part of it, or before you are going to use it, get out these rare earth elements, which are only found in China now, and might be strategic things in the future. So we think about it, and also with treating the wastewater, let's say, getting out the metals, it's a really good source for new metals. I mean, with 1 gram of zinc in the water, you have a source for zinc. Problem is that when you, let's say, want to go to a refinery, they say it's waste, and then you have to pay extra. So there are some things that have to be changed in the law and in the regulations. Yes.
Thank you.
Yes. Very interesting question. Thank you.
we have got to finish, as we will be cut off very shortly. So I would like to thank all the speakers and for your patience, and I would like to encourage you to stay on for the session 6, which is about LNAPL and chlorinated compounds remediation. So another great session following shortly. So thank you very much to everyone, and sorry about the technical issues. Cheers.
Thank you, Nicole.
Thank you.
Bye-bye.
Bye-bye.
Thank you.
Bye.
Thank you.
Thank you from my side as well.
Thank you.
Nicola.
Thank you very
Thank you,
much.
Marco, for jumping
Bye.
in.